Hello, my name is Kees van den Doel. I'm with Adrock. We're a company based in Scotland. We're specializing in subsurface exploration using low-frequency electromagnetic waves. In this talk, I'll be discussing subsurface temperature measurement using electromagnetic waves and machine learning with applications in enhanced oil recovery. Outline of my talk, I'll give some background and motivation for this work. I'll explain our electromagnetic system and how we combine it with borehole field measurements to set up a machine learning architecture where we basically train our collection of neural networks to interpret electromagnetic data and extract temperature information from it. I'll give you some results to look at, and I'll give a discussion of the results. What's enhanced oil recovery? It's basically any method that improves over drilling a hole and hoping the oil will come out by itself. So how does oil come out? Well, it flows, and that means oil that's has low viscosity is easier to extract. So most methods, all methods of enhanced oil recovery really increase the mobility of the oil by reducing viscosity. And an obvious way to do that is by heating it up. It's like honey, it becomes more liquid. It can also be done with gas injection. Apparently, I don't know much about this method. We've been focusing on thermal methods. So a very common method in these oil fields is to use steam injection to increase the temperature and basically liquefy the oil, and it collects in an underground puddle, and then you just suck it up. So it sounds simple, but it's of course a quite involved process. So we have to make sure the temperatures that are generated by the steam injection are correct, and they are at the right location. There's no leakage, and we're not heating up something we don't want, causing collapse and possible accidents at various places. So we have to know what the actual temperature is in this whole process. And the common method of doing this is to use temperature observation wells, which I'll abbreviate by TOWs in this talk. So it involves drilling a hole and sticking a thermometer in there and lowering it and taking your temperature measurements. Very straightforward, but it's expensive. So expensive that it's typically done only 3 to 4 times a year for each well. And why is it expensive? Well, you have to drill the observation well itself. Then once that's done, a measurement itself is typically cost about $5,000. And there's the well has to shut down during the measurement. So it's quite an involved process. That's why it's done only 3 to 4 times a year. But it would be very nice if you could do this more frequently, because if something happens in the intervening months, it can cost a lot of money and actually cause harm to people as well if something goes wrong. So how would we ideally like to measure these subsurface temperature? Well, we don't want to have any drilling, using only surface data. We want to obtain the temperature without well downtime. The acquisition should be fast, and so we can do it more frequent. All this, of course, results in low cost per measurement. Finally, the data processing should be easy in the sense that we can basically feed our data to a system and hit return and get the results we want. It should not involve scientists racking their brains on how to interpret the data. What does our electromagnetic data look like? Well, we operate a pulsed radar subsurface imaging system. It operates somewhat similar to ground penetrating radar, but there are also differences. And the main differences is the low center frequency we use. For ground penetrating radar, this is typically like 30 megahertz at the lowest, quite often higher. Why? Because you need high frequencies and small wavelengths to image small objects, which is usually the goal for GPR applications. Low frequency pulses, like we're using, have been used in astrophysics or in space exploration. There is a radar system like this, somewhat like this, the Mars system orbiting Mars, and it shoots radar waves at Mars, collects data and images the subsurface down to several kilometers. But the low frequency is necessary to get deeper penetration in these kind of lossy environments. So our data acquisition is bistatic, which means that we have an emitter and a receiver. The receiver records time domain traces of data that comes back, backscatter essentially, after we send radar pulses down into the ground. Or because the electromagnetic waves propagate really quickly, so a measurement takes of the order of microseconds, even taking into account delays because of software problems or issues. But we can easily stack 100,000 measurements in, say, 1 minute. We've gone up to 1 million measurements for data for noise reduction. The data that we acquired to develop this system was acquired on 2 large producing oil fields. On one we had access to 21 temperature observation wells, and the other 40. And we took our system there and took our electromagnetic measurements near those wells. We also had 3 wells that were measured from a 3rd oil field. Of course, 3 wells is not enough for any kind of machine learning, but we did this to test if the networks that we trained on the other wells could be used to predict temperature from another location. We did not expect it to work, and it didn't work. So the principle is quite simple. We have our measured data, and we have the ground truth TOW data, temperature observation well, and we have to the electromagnetic data is, maybe I should show you this slide first. The electromagnetic data comes from backscatter. So we see here our picture of our system. The blue arrow is basically the pulse that's traveling down, and all those sort of wavy lines, they represent small irregularities that determine how much backscatter and what kind of frequencies, etc., what the nature of the backscatter at a particular location is. And so while this pulse travels down, at each location there is backscatter, which are the red arrows, and they're collected in the form of a time series. So since both data are time series, the machine learning is fairly straightforward. We can use existing tricks and methods. We didn't have to invent a whole new machine learning approach. We basically want to predict temperature from electromagnetic data. The electromagnetic data depends on primarily on the geology, on the subsurface structure. And the subsurface structure determines basically the electromagnetic properties such as conductivity and permittivity of the subsurface, and that, or variation in those quantities, determine backscatter. Now, those quantities are strongly affected by temperature, but not in a way that's easily quantifiable. It's not even known in those environments what the precise relation is. So we get this time series, and we know there's information about geology in it, and also about temperature, and we have to separate them somehow. And so we've done, that's basically the goal of our machine learning approach. So first of all, we compress our temperature observation well data into an autoencoder network to simplify the task of the final network. It turns out with just 5 numbers, you can get a pretty good parameterization of the temperature profiles, because the temperature profiles are not random. due to steam injection. So if there's no steam injection, it's just a standard gradient, slowly increasing temperature with depth. But if there's temperature injection, there's a hot zone, which typically has a beginning, an end, and a peak. So with those 5 numbers, the autoencoder network can pretty much compress all the data of the temperature, of all the temperature logs in an oil field. So that means we now have to predict those 5 numbers from our electromagnetic time series and train our network to do that. So we call the data that we're getting from our radar system after some signal processing and pre-processing, filtering, etc., called M. That actually stands for modulation with a particular type of signal processing, which is common in imaging and photometry. So, so we have data on the site with 21 wells and one with 40 wells. So we train separate networks on there, and we use the common approach of training, say, on 39 pairs, and then predict the remaining one, and then repeat by excluding everyone to get sort of a simulated blind test. There were 3 sites that were from a third field that we did not use in training because we had only a little bit of data, and we did not expect to get reasonable result there, which is confirmed by our data. Showed that already. So here's our autoencoder. We take our measured temperature, we encode it down to what turns out to be 5 numbers, and we save the decoder. So now from those 5 numbers, we can predict the temperature. Then we take our data, M, and we feed it to a feed-forward neural network, which does supervised learning on the 5 numbers from the encoded temperature wells. And we fiddle with it. There's many parameters to adjust, of course, but those are technical details. First of all, here's the data from the autoencoder. So the red ones are the actual temperature profiles, and the autoencoder predictions using only 5 numbers are the blue ones. So we see it's fairly accurate. There's one outlier, the number 18, sort of in the middle. Turns out there was actually a problem there with the temperature observation well. So here are the results for the first test, which had 21 wells. And so we picked 20 out of the 21 and exclude 1, and that's our blind prediction. So most of them are quite well. There are some exceptions, like 20 is the only real failures, but encouraging results. The green ones are the wells from the third site where we did not have enough information to train. So we trained our network on the big site with 21 wells, and then applied it to the other with very bad results. And that's as expected because the geology is different there. And our network was just trained to distinguish geology from temperature in that particular environment. And here's a second set of results for 40 wells. Mixed results because the field is not as homogeneous as we would like. So we believe these results are still generally encouraging, but we need more information fed to the neural network to distinguish the geology better from the temperature data. So I've said most of this already. The question is now how do we move forward? So we've assumed, the network assumes the ground conditions are homogeneous, but they're not. So the obvious thing to do is to feed additional information based on the geology to this, which we are currently developing. Why does it work? Well, the electromagnetic waves apparently penetrate sufficiently deep, not deep enough that you can see actual reflections like in GPR, but enough to give us data to work with and predict temperatures reasonably well. Thank you for your attention.